Am I audible from your side?
Yes, sir.
Is my slide is visible?
Yes, sir.
Okay. So, so we're discussing about rotating variable differential transformer. So in my last class, we discussed about that LVDT. Okay, so where you are making that coil fixed positions, but you are changing the positions of the core, means movable cores are there. Okay, by their changing of the movement, so your induced voltage, you can see your voltage is induced in your secondary path. Okay, now you are getting the differential voltage, means whatever voltage you have induced here, so we are subtracting them and we are getting that value. Okay, like V out equal to VA minus VB, like that we are getting. Okay, so it is rotating rotary variable differential transformer. Okay, but the linear one, what was there? So only one core is there. Here you can see the core. Okay, if the core is moving, so automatically their values of induced EMF is changing. Okay, so that meet conditions you can consider that nominal. So why it is zero? Okay, core at O position, so induced EMF E equals to zero. Okay, basically both of the side you can see the cutting of flux is same. Okay, if the cutting of flux is same, okay, so induced EMF magnitude also same. Okay, so V equals to VA minus VB. So both of the side VA and VB is same, so they are zero. Okay, so in these conditions you can see, so there is no points, means you can say negative. Okay, so VA is zero, basically there is no cutting of flux of the core. So this negative point only there, VA minus VB. So VA is 0, VB you are getting some value. So starting from negative voltage. Okay, so you can see over there starting from some negative voltage. Then these conditions only positive side you have it. Okay, negative side is 0, so no cutting of flux. So directly positive side. Okay, like that. So today we are discussing about the capacitive transducer. So capacitor having three common means two plates, normally two plates. Okay, so two plates means you can change their durations, means you can change the distance between two plates or separation between two plates, means you are arranging the transducer such a manner if any of the parameter is changing, so the voltage due to the capacitor means stored energy that also been changed. Okay, charge change. So principle of this type of variations in the capacitance are used to produce the measurement of many physical phenomena. So, okay, such as dynamic pressures. Okay, so due to pressure, what happened? The plate movement, maybe their plate movement or cross sectional area changes, or you are changing the dielectric. So you can see the changes. So dynamic pressure, displacement, it's possible force and humidity. Okay, so due to several changes, so the values of the capacitance may change. Okay, and if that values are changing, so that C value, if it is changing, so definitely that other parameters also changing, means charge is related to your capacitor, so everything will be reflected over your value. Okay, so here you can see C equals to that, and conditions some constant value is given k 0.88 k n minus 1, so number of plates actually. Okay, number of plates n equal to number of plates. The generalized equations equation capacitance. Okay, D is that separations of plate surface, K is the dielectric constant, K equal to for air, K equal to 1, A equal to area. Okay, so these are the basic considerations you have considered. Okay, so here you know that C equal to Q equal to CV. Okay, so C equal to Q by V. If your value of C is changing, so automatically if the any of the parameters are changing, okay, due to some pressures, displacement, so your C value changing means other parameters are changed. Okay, so capacitance in the ability of a body to hold the electrical charge. Okay. Capacitance is also measure of the amount of electric charge stored for a given electric potential. Okay, so it's charged, so given electric potential. A common form of the charge storage device is a two-plate capacitor. Okay, so two-plate capacitor common form, you know that if the change, so if the charges on the plate are plus Q to minus Q, changes are there from plus Q to minus Q, and V gives the voltage between the plates, then the capacitance is given by C equal to Q by V. And it's the definition of the farad you are getting from here, 1 coulomb per 1 volt. Okay, definition of farad. Okay, so now what happened? So here you are going to measure the capacitance. Okay, so some liquids are there, hollow tubes are there, and central electrodes are given. Okay, now some of the openings means you are giving the electrolysis type of thing, means not directly electrolysis. So electrodes are there, liquids are there. Now we are finding that value. Okay, so capacitor transducer, how it will work? Capacitance, pick up the pressures, sorry, pick up the measure liquid level. Okay, the liquid level you are able to measure. So changing dielectric constant, how? Basically changing of the dielectric constant. Suppose there is air, okay, in between there is air and the liquid. Okay, if the level of the liquid has changes, so definitely that values are changing. Basically dielectrics medium, you know that air and fluid are there. So, okay, so the area of the dielectrics, so area of the air and area of the fluids both are changing if fluid level is increase or decrease. Okay, due to changing of the dielectrics, automatically the capacitor value C has been changed. Okay, if it has been changed, so automatically it will reflect it to the stored energy and the potential across appear across it. Okay, the above figure, okay, from the figure it can show that device used for the measurement of liquid level in a container. You can see the container. The capacitance between the central electrode and the surrounding hollow tubes varies. The changing of dielectric constant brought about the changing of the liquid level. Okay, so due to changes of the liquid level, your dielectric constant value has changing. Okay, thus the capacitance between the electrodes is a direct indications of the liquid level. Okay, so variation in the dielectric constant can also be utilized for the measurement of the thickness, density, etc. So we are able to measure all the parameters. So how do you get the parameter? Your equivalent parameter. So how much changes of that capacitor value? So the length changes of the length of the liquid. Okay, so how much C values are changing and equivalent voltage levels are changing. That's the important point. Changing of the due to pressures or due to pressure or due to changing of the level, so your voltage level is different changing, that you need to know. Okay, so capacitive transducers are there. So capacitive transducers, so torque meter, here you can see the torque meter. So slips are there, so thick, you can see teeth. Okay, so different teeth are there. Okay, teeth of the rotor gap, teeth of the rotor, so air gap is there. Okay, air gap is there, so internal membrane and slab. Okay, so both are there. So changing of that, changing of the air gap, definitely the capacitor is also changing. Okay, so rotations can be possible both the directions. Okay, anti-clockwise or clockwise. Capacitance changes. Okay, capacitance changes depending on the change of the effective area. Okay, so that effective area may be changed due to rotations. Okay, this principle is used in the secondary transducing element of a torque meter. This device use a sleeve with the serration skirt auxiliary and the matching internal membrane with the similar serrations as shown in the above figure. So here you can see the orientations. Okay, from unequal, sometimes air gaps are there, unequal. So if it is rotating, so air gap also changing. Torque carried by an elastic membrane cause a shift in the relative positions of the salutations, thereby the changing of the effective area. So if the changing of the positions may cause for changing of the area over there. Okay, the resulting the capacitance change may be calibrated to read the torque directly. So you are able to get the torque directly. So how much values are there? You have to first make a data sheet. Okay, after data sheet you have to derive that value. Okay, by that way you are only getting that results. Okay, so capacity transducer for pressure transducer. Okay, for the pressure you are getting the value. So similarly the below is there, means a membrane is there. Okay, so and you can see the air gap means the plate difference. Okay, so that capacitance you are going to measure in between two plates. So one membrane, another one is electrodes is there. Okay, another electrode, so fixed electrode. Okay, so what you are called, so below diaphragm membrane, whatever is there. Okay, so here give the pressure force over there, so automatically the membrane is vibrating. So if they are vibrating, so their upper surface will be changing. Okay, so deformed it. Okay, due to pressure the membrane is deformed. Okay, if it is deformed, so automatically the plate length, sorry, the gap between two plates, okay, that also changing. If that gap is changing, so then what happened, that value also been changing. Okay, so you can see the capacitance. Okay, change of that clearance D. Okay, so D clearance is there, so that area is changing, that length is changing, so clearance D also been changing. Okay, if it is changing, so so capacitor value also changing. Okay, the capacitance varies inversely, the capacitance varies inversely as the distance between the plates. So varies, so distance between the plates. The figure shows a capacitive type of pressure transducer. Okay, pressure transducer where the pressure applied to the diaphragm changes the distance between the diaphragm and the fixed electrode, which can take the measure of the pressure. Okay, as the changing is there, due to their changing, so diaphragm movement is there, so automatically the capacitor value is changing. Okay, so it's a very sophisticated devices. By using the capacitor transducer working on it, so it is very sophisticated. So minimal changes, the charge are changing. Okay, so minimal changes, very sensitive. Okay, so that's why it is very costly also. Okay, what are the advantages are there? Okay, so advantages you can see for capacitive transducer. Number one is that required externally small forces. Okay, requires extremely small forces to operate and highly sensitive. That I am telling. Okay, so that's why it is very costly device. That is another disadvantage. Okay, so they have good frequency response where the useful dynamic measurement means very minimal changes you can observe their response, you are getting some of the response. Okay, high resolution can be obtained, high resolution can be obtained. They have high input impedance, hence the loading effect are minimum. Okay, loading effect is minimum. This transducer can use for the application where stray magnetic fields render with the inductive transducers. Okay, so you can see some of the important advantages over there. Okay, disadvantage, definitely there are some disadvantages. First disadvantage, it is not cost effective, basically very costly device. Okay, number one, then metallic part must be properly insulated, that I am telling, very sensitive, so there is a huge chances for means bypassing the charge. Okay, what is charge bypass? Basically you know that means plus 2 level idea. Now it is not in plus 2, it is in below, means SSC. Okay, so all the students known about that conductive means frictional or static electricity and conducting electricity. Okay, so capacitor normally you are getting, that is not for, you are getting it for normally static electricity or the friction electricity. Okay, for the fractional electricity, what happened? That charges are not able to conduct from one place to another place. Okay, basically you can see the charges are normally you can observe in inside of that insulator. Okay, surface of the insulator means whatever things are there, charges are there. Okay, they are not able to passing. Okay, passing or flowing one place to another place. It is not possible for this static electricity. Okay, that's the one fundamental features of the static electricity. That's the theory. If you are using the metals, okay, sorry, insulators are there. Also, you are using sometimes the metal. Somehow, if they are connecting, so that additional thing it will be drained out. Okay, additional thing it will be drained out. So it is not good for that use. Okay, so that's why sorry, not good for the use, and then it's good for the use, but you have to take the proper prevention. Okay, if the proper insulation is not there, then your system, your electrodes will be biased by that external fields. That is number one. Another two is that automatically charge will be passing through that electrical path. Okay, that is another problem. Okay, so that properly insulation is required. They show the non-linear behavior. All the transistors, most of the transistors are showing non-linear behavior. Okay, to the edge effect, ground guard rings must be used for the eliminate that effect. Okay, so guard ring means charging current is flowing from that unwanted path. Okay, so what you need to do, you have to counter the charging current. So that's why guard ring, okay, it's required. Okay, sometimes they are sensitive to temperature affecting their performance. Okay, sensitive to means temperature effect, so it will have a direct effect on their performance. The insulations carry circuitry. Okay, these transducers are complex. Okay, capacitance of this transducer may change the presence of the dust particle and moisture. Okay, so if there is a presence of moisture and dust particle, automatically that mu value will be reduced and capacitor you are getting less capacitance. There is a huge chances for the puncture. Okay, that's why in transmission line means we are using that insulator plate. Okay, everywhere you can see any long line transmissions. Okay, means substation. So regularly you have to maintain them. There should not be means what happened, the moistures are there as well as the dust are also sedimented means upper portions of your insulator. So regularly you have to clean them. Otherwise what happen? Otherwise after some time it will be punctured. Your discs will be punctured due to dust. What happen? Their R value means insulation value is reduced and charging current are maybe damage or you are burn out. Okay, burn out your insulation. Now piezoelectric transducer. Piezoelectric transducer, what happened? There is a crystal. Okay, so you are using some piezoelectric crystal over here. Okay, this is your piezoelectric crystal. Now you are providing the force. Okay, you are providing the force due to the presence of force. What happened? That EMF will be output voltage air gap. Sorry, output voltage gap E will be developed. Means EMF will be developed. Okay, so you have to find out that equivalent space sorry equivalent pressure and that EMF generation. So we have to make a table or data sheet for it. Okay, so in piezoelectric crystal what happened, a piezoelectric transducer what happened, certain materials, okay, certain materials can produce an electrical potential when subject to mechanical strain. Okay, subject to mechanical strain or the conversely can change the dimensions when the subject to the voltage is called the piezoelectric effect. Okay, if any due to mechanical force, what happens? The pressure is there, pressure is appear across your or crystal, and due to pressure, you can see that some of the EMF are EMF are producing. You can see some of the EMF is generated due to pressure. Okay, so it's an example of a transducer for measurement of what pressure measurement. Okay, this figure shows the piezoelectric crystal. Okay, placed between the two plates electrode, and when force F is applied to the plates, a stress will be produced in the crystal. Okay, and the corresponding deformations. The induced charge, how much value of induced charge? Q equal to D into F, where D is that piezoelectric constant. Okay, in output voltage E equal to GT into P. Okay, T is the crystal thickness, P is the impressed pressure, and G is called the sensitivity given by G equal to D by E. Okay, how much distance whole divided by E. Okay, being the strength. So I hope all of you will understand what are the most important features of the piezoelectric transducers. Okay. So piezoelectric materials, transducer materials that very common one is quartz. Okay, you are using that quartz, and most commonly used or suitable used for the electronic oscillator. It is its output is also low but stable. Okay. Next one is the Rochery salt. Rochery salt is the potassium sodium titrate. Okay, Rochery salt is potassium sodium titrate. So if you give the pressure of this crystal of that quartz crystal or Rochery salt crystal, okay, that you can see some voltage will be appeared across your crystal. Okay. Then natural provides the highest output. Okay, it gives you the highest output, but require protection from moisture and air. Cannot exceed the temperature level above 45 degrees centigrade. So you have to take care about that salt and prevent the temperature. Prevent it from the moisture, otherwise it is high, means there is affinity with the hydro, so automatically it can means intake the means moisture from the environment, so you have to make the protections for it. Barium titrate, okay, so aluminum dihydrogen phosphate, another example, and ordinary sugar, it's also piezoelectric material. Okay, the desired properties of the stability, high output, and insensitivity to temperature. That's the benefit. Humidity, okay, and the ability to be formed into the desired shape. Okay, so if you are able to change the shape also, your desired shape. Okay. So barium titrate is the polycrystalline. Okay, thus it can be formed into a variety of size and shapes. Okay, so it's crystal having varieties of size and shape, and you are able to you are able to use it for your applications. Okay, so piezoelectric transducers are normally used for measure the surface roughness. Okay, strain, force, torque, pressure, motion, and noise. Okay, simple thing. Physiologic transducers, what happen here? You can see one diagram. So, sorry, this is not piezoelectric, this is photoelectric. So you can see the diagram. Okay, where light is or photo emission happen to that cathode of that piezoelectric material. Okay, so here you can see anode is there. Okay, and anode is positive, cathode is negative. Okay, so direct light is falling down to the cathode. Okay, so the photoelectric transducer convert a light beam into the usable electrical signal. So whatever that I am taking example optoisolator. So what you are doing? So due to current flowing through the circuit, okay, inside of the optoisolator there is a all the time there is a LED. Okay, that LED light is emitted to the base of that optoisolator. Automatically voltage will be developed. Okay, so that's why it is called that usable the electric signal as shown in the figure. Light strike to the photoemissive cathode. Okay, photoemissive cathode releases the electron which are attracted towards the anode, therefore producing the electric current in the circuit. So opposite directions of the electron, the current is flowing through the circuit. Okay, the cathode and the anode are enclosed in a glass or quartz envelope. Okay, so for the protection purpose. Okay, which is either evacuated or fulfill with an inert gas. Okay, so that portions, what happened normally you are not connecting with other gases, so they are having property in high temperature that can react with other components. Okay, their chances are there. So what you need to do, so you have to sorry, you have to who means protect, you have to give the protections. Okay, so here you can see the photoelectric sensitivity given by the expression. You are able to see I equal to S into phi. So what is phi? This is illumination. How much strength of current is there? Okay, light strength. S is sensitivity. I is that how much photoelectric currents are there. Okay, the response of the photoelectric tube to different wavelengths is influenced by, so what are the causes for the influence? Means the transmission characteristics of the glass tube is envelope. Okay, photo emission characteristic of the cathode material. So these all are the most important portions. So how it will work? So first, what you need to do, you have to do some isolation or some of the portions as isolation some of the circuits. So this very good you implement, basically isolate between input and output, so that no direct electrical connections are there. Okay, so only that magnetic connections are there. Okay, so from the diagram we can also understand what are the important features of that features of the photoelectric transducers. Okay, now photoconductive transducer, what are the important points are there? The principle of this transducer is when the light strike the semiconductor. Okay, light, light strike the semiconductor and its resistance is decreased. If the resistance is decreased, so what happens? So resistance is decreased means it will producing some EMF. Okay, and that EMF you are able to measure or whatever. If you connect the path outside, connect the path. Okay, so automatically some of the current will be flowing there. Okay, and you are able to see that how much current is flowing over there. So I hope all people are able to understand that what am I telling. So another digital transducer, that portions I have already discussed some initial classes. Okay, so opto isolator is there, optical isolation is there. It's an RPM meter, means tacho generator. Okay, so what is the purpose of this one? So tacho generator is able to tacho generator is converting the speed into the EMF, and you can check from your data sheet how much speed means how much RPM stands for what. Okay, so based on that you can tally it and point out it, and you are able to get the value. Okay, so as simple as it. And for analog signal, definitely it is better than your digital signal. Okay, so in digital signal, sometimes that digital selection, so sometimes reconstruction problem is there, sometimes transportation delays are there, so different additional unwanted problem is there. So operating range goes to be very high. So what we need to do, we have to go for so that I am telling that digital sensor if you use, so directly other circuit you can omit. Okay, so omit means directly isolation circuit you can omit one of the isolation. There are normally two of the what isolation path isolation circuit. One is your before before costly devices. Okay, costly device means costly measuring devices like opality, displays. Okay, so that you need to give. Another throughput is there, so three different channels are there. Based on that channels which gives you better response. So the means whatever response you will get, you can see it. Okay, if you have display, so you can see it. If you have oscilloscope, you can visualize that one. Okay, so then after that we can see about that Hall effect sensor. So in case of Hall effect sensor, we are measuring the pressures. Okay, so pressures are there. Okay, so based on the pressure you are able to measure it. So normally Hall effect sensors in our electronic circuit, we are it is very common to use Hall effect sensor. We are using LEM based Hall effect sensor for current sensor, voltage sensor. So their ranges are also very high. Okay, so how much ranges, as well as they are very costly. Okay, so how much it is there, so based on that you are able to get that value. Okay, so what happened in Hall effect sensor? So in Hall effect sensor, there is a north pole, north pole and south pole. You are connecting your circuit over here. Okay, 2 to 4 it is there, so some sources are there, so currents are flowing over there, and due to that positions, due to its presence position, there is a cutoff flux. Okay, due to cutoff flux you are able to see some of the magnets, and that is interacting with your own magnets, and you are able to get that value. The presence of magnetic field deflects the electron flow. Okay, those are the conducting materials. Okay, the electrons move one end and conducting materials. Okay, so developing in the directions perpendicular to the gross current flow. Okay, so based on the direction, particularly current carrying direction, you can see, and potential indicates the strength of the magnetic field, how much values are coming. So based on that you are calculating or the processing of that means processing of your magnetic field. Okay, so how much values are there, you will enhance the quality of the strength of the signal. Okay, and if you have that good strength, so you are all of you visualize or understand easily. Okay, applications where you are going to use IC engines, electronic ignition system you are using over there. Okay, so used to determine pressure, you used to determine the positions come the shaft. Okay, that you can see. Okay, so you can also see first one is that position of the shaft. Second one is that magnetic. Okay, so position of the magnetic permanent rotor. That is also possible. Then next point is that positions and the velocity. Okay, how much is position, how much is velocity. Okay, that you are able to measure. Current sensing IC is means electrically isolated alternating to shunt resistor. So if there is a isolation, so any of the fault is occur or power circuit, okay, or control circuit, nothing is replicated to the power circuit, but voltage divisions and voltage rating and powers of the control circuit is very less. So it's almost negligible compared to your means means normal conditions. Okay, when you are able to measure that oscilloscope. So so how much the means how much values are there. Okay, so based on that you are able to, so there is a isolation. Okay, so optical isolations normally we are doing for this study. Okay, so Hall effect sensor type, what are the different types of there? So pressures of the magnetic field, there are Hall effect sensor, the output is proportional to the magnetic field strength. Okay, if your magnetic field strength is increasing, automatically output EMF is increasing. Okay, the Hall effect of digital switches having important features, that is magnetic field above the threshold turn on voltage. Okay, so it's required. Second one, presence of magnetic field below the threshold turn of voltage, just like your Smith trigger. So maximum how much it can go, that current, and next one how much it can, means tolerable region, maximum current, minimum current. Before that means below of that rating, it will not work. Okay, Hall effect, digital latches are there. Okay, so we know that different types of latching device like JK flip flop. Okay, so AND gate, NOT gate. Okay, so different different we are means using latching. Sorry, we are using so. Uh, so we are using that different types of thing. Latch on and latch off means, so when it will be turned on and turned off, that will be decided by the Hall effect sensor. Basically it is sensing the voltage and current rating and drastically reduce that value. Okay, after that you are processing the value, and finally before means before for giving the signal to that one, so you will amplify the signal strength and you are able to calculate that value. Okay, so packing and manufacturing. So as per their IC shape and size, okay, they are numbered. So you are manufactured them. Okay, so different companies are there like Honeywell. Okay, so they are actually packaging and manufacturing the sensors. Okay, implementations where you are going to implement. So normally we are going to implements for sensor temperature variations. Okay, critically accuracy to reduce the error. Okay, sometimes some sensor having that error, so you need to reduce that value of the error. Some Hall effect sensor detected presence ferromagnetic material or not the magnetic material. So as it is not connected in the magnetic material, so all the material should be ferromagnetic. Okay, so not exactly that one. Okay, variable reluctance sensor. Okay, so I'll start discuss about variable reluctance sensor in my next class. Next class means Monday we will discuss start and discuss about this value. Okay, Hall effect sensors, you can see example of a LEM sensors. LEM sensors are the Hall effect sensors. Okay, so we can we can see that LEM LV25P, it is Hall effect voltage sensors. Okay, so LA15, sorry, LA15, so it is a current sensor. Okay, so different sensor you can see over here. Okay, so I hope you are able to understand. Is there any confusion?